how many full adders are required to implement ripple carry adder? Suppose I want 4-bit ripple carry adder. How many full adders are required? Tell me any of you. Please respond. So for 4-bit ripple carry adder, we require 4 full adders. Then what is the major problem with the ripple carry adder? So that is the, propagation delay. Okay, that is the carry propagation delay. Okay, so even though the two input bits A and B are ready, the full adder can't perform the addition operation. Why? Because it requires carry input. Okay, so until unless carry will not reach the next full adder, the next full adder will not perform the uh, I mean addition operation. Okay, so that is the main problem with the ripple carry adder. Even though the input bits A and B are ready, the full adder cannot perform the addition operation. Why? Because it has to wait for the carry from the previous full adder. Once the carry from the full adder comes there, then only the present full adder performs the addition operation. Okay, so that is the main problem with the ripple carry adder. So that ripple carry adder problem can be solved by using the carry look ahead adder. In carry look ahead adder, we will find out the carries well before the addition operation. Okay, initially itself we can determine or we can find out the carry of all full adders. Okay, then how to find the carry priorly? In prior to the addition operation for all full adders. How means already we have studied full adder. Full adder means how many inputs are they? Tell me. For full adder, how many inputs and how many outputs? So full adder, the number of inputs are 3, the number of outputs are 2, the outputs are sum and carry. Okay. So by using the carry expression of the full adder, we can determine the carries of all full adders, carries of all full adders before performing the addition operation. Now we'll see how to determine how we can find carries before the addition operation. Okay, this is the already explained. So carry look at adder. First we'll see ripple carry adder. What is the problem with the ripple carry adder and how it can be resolved by using carry look ahead adder. CLA short form. Okay, so already we know this table. This is ladder output table. 3 inputs and 2 outputs. Okay, the outputs are sum and carry. So what is the sum expression? Tell me if the ladder is having 3 inputs x, y, and z. What is the sum expression? Any of you please tell. So the inputs are x, y, z. The sum expression is x, xr of y, xr of z. What is the carry expression? Carry expression is xy plus yz plus zx. So we can also write carry expression in another way. That is x xr of y into z plus xy. So here the inputs are A, B, and C in. The outputs are S and C out. The carry out can be written like this: AB plus B into C in plus C in into A. Other way of writing carry expression is carry expression of a full ladder is A XR of B into C in plus AB. Okay. So this is the sum expression. This is the carry expression. Okay. We use this carry expression to determine the carries of all full adders well before the addition operation. Okay. So that is what is the carry look ahead adder. Okay, why? Because the main problem in ripple carry adder is the full adder has to wait for the carry input. Okay, to get rid of that, we can find out all carries before the addition operation itself. Okay, so now if we see C out, this is the C out expression. Now, if we go back, it is having this is the let us consider 4-bit adder. Okay, 4-bit adder is having 4 full adders. Now first we'll find out this C1 of this full adder 1, C2, C3 and C4. How we can find, we'll see. Now if we see now full adder 1, okay, of a 4-bit adder, the carry output C out is C1. Okay, for first full adder, what is the carry output? That is C1. C1 is equal to, it can be written as, for the first full adder, what are the inputs? A0, B0 and C0. What is the carry expression? C1 is equal to A0 XR of B0 into C0 plus A0 B0. Okay, so this is the carry expression of the first full adder. For first full adder, the inputs are A0, B0 and C0. The carry output is C1 is equal to A0 XR of B0 into C0 plus A0 B0. Now we can define two terms. They are, the two functions are the two terms. They are generator term and propagation term. Okay, we can also call them as function, generator function and the propagate function. So propagate function means, why we are using this propagate function means, this propagate function can also be used to determine the sum of a full adder. If we consider any full adder, we are having carry and sum. Okay, when we propagate this propagation function means, we will propagate this propagation function to determine the sum of a full adder also. Okay. So now this generator function generate gi is equal to xi into yi, propagate pi is equal to xi xr of yi. Now if we can express C1 in terms of G and P, that is, now to express that one, G naught is equal to X naught into Y naught, P naught is equal to X naught XR of Y naught. Now what is C1 is equal to, already we have written C1 is equal to A naught X naught, A naught XR of P naught into C naught plus A naught B naught. Now in place of this A naught B naught, we can write down G naught. In place of this A naught XR of P naught, we can write out, we can write down P naught. In that way, C1 is equal to G naught plus P naught C naught. This is the carry of the first full adder. So similarly, what is sum expression? Already we know. So without understanding full adder operation, we can't understand the operation of carry looped adder. First of all, we should know what is the full adder, how many inputs, how many outputs, and what are the expressions for sum and carry. We should know all of them. Okay. So now what is the sum of the first full adder sum expression? It is equal to S naught is equal to A naught XR of B naught XR of C naught. Now what is A naught XR of B naught? That is equal to P naught. Now sum S naught is equal to P naught XR of C naught. This is the sum expression of first full adder. This is the carry expression of first full adder. Okay, why? So C naught is already known. C naught is already known. In general, C in is equal to C naught. That is equal to 0, grounded. Okay, initially. Next one. So for second full adder, same thing. Now tell me, any of you, what is the carry expression of second full adder? Please unmute and speak. For full adder 2, the inputs are A1, B1 and C1. Tell me what is C2 is equal to expression. Please unmute and speak. Don't sleep. Even though it is afternoon. Okay, the expression C2 is equal to, this can be written as A1 B1 plus B1 C1 plus C1 A1. That can also be written as C2 is equal to A1 XR of B1 whole into C1 plus A1 B1. Okay, that is what is here. Now what is G1 is equal to, that is XI by N. So that is A1 B1. What is P1 is equal to A1 XR of B1. Now we can express C2 in terms of P1 G1. C2 is equal to P1 C1 plus G1. Okay. So now we can also to find C2 we should know C1. To find C1 we should know C0. So that's why I will express C1, C2, C3, C4 in terms of C0. Okay, why? Because C0 is known initially itself. Okay, so that's why even though I'm getting C2 in terms of C1, I will try to express C2 in terms of C0 also. That is, in place of C1, substitute this expression, that is G0 plus P0 C0. Substitute here G1 plus P1 into G0 plus P0 C0. Now try to expand. That is C2 is equal to G1 plus P1 G0 plus P1 P0 C0. So this is the carry expression for the second full adder. Now what is the sum expression for second full adder? S1 is equal to, the inputs are A1, B1, C1. The sum expression S1 is equal to A1 XOR of B1 XOR of C1. Okay, now we can also express S1 is equal to in terms of P1 and C1. That is A1 XOR of B1 is equal to P1 XOR of C1. So these are the sum and carry expressions for full adder 2. Now come to full adder 3. So for full adder 3, what are the inputs? The inputs are A2, B2 and C2. Okay, the outputs are C3 and S2. Okay, now what is C3 expression? C3 is equal to G3, C3 is equal to G2 plus P2 C2. Okay, so what is G2 is equal to A2 B2. What is P2 is equal to A2 XOR of B2. Now in place of C2, substitute this expression. That is G2 plus P2 into, what is C2 is equal to G1 plus P1 G0 plus P1 P0 C0. So when you substitute this expression, what is C3 is equal to G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. So this is how we can express the carry of the third full adder in terms of C0. Okay. So why we are trying to express these can be determined. So we can determine G2, P2, G1, P1 readily. Why? Because we are ready with A1, A1, A0, A1, A2, A3, and B0, B1, B2, B3. We know all those inputs. So when we know all those inputs, we can determine P1, G1, P2, G2, P0, G0, and P3, G3. Okay, and what is the unknown thing here? Carry from the previous input. That's why we are trying to express the present carry in terms of the initial carry. That is C naught. C naught is known. That is in general grounded. Okay, so that's why we are trying to express C3. Why? Because these things and all you can determine. Why? Because inputs are ready already. They are A and B. A is equal to A3, A2, A1, A0. B is equal to B3, B2, B1, B0. Okay. Similarly, what is the sum expression of third full adder? S2 is equal to A2 XOR of B2 XOR of C2. This can also be written as P2 XOR of C2. Okay. Now, similarly for the full adder 4. So this is the carry expression. C4 is equal to G3 plus P3 C3. So what is C3 already? We determined. This one. Now try to substitute this expression in next one, that is P3 into C3 is equal to G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. So after substituting this one, finally we got the carry expression for the full adder 4. If you see here, we don't have any carry from the previous full adder. Okay. In general, what is the carry from previous full adder? That is C3. But we express C3 in terms of again C0. Okay, you know all these things G3, P3, G2, P2, G1, P1, G0, P0, and C0 is also known. So this C4 in terms of the known quantities. What are the known quantities here? G3, P3, G2, P2. Here, what are the known quantities here? So don't forget about the C3. Look, think that you are at full adder 3 directly, full adder 4 directly. So when so that's why somehow we have to express that C4 in terms of the known quantities or known things. Okay, what are the known things here? G3, P3, G2, P2, G1, P1, G0, G0, P0, and C0 is also known. Okay, in that way we can directly determine carries of all full adders initially self. Okay, so this is what is nothing but the carry look ahead order. We can determine all carries well before the addition operation. Okay. Now, what is the sum expression of the last full adder? S3 is equal to A3 XOR of B3 XOR of C3. Okay, that is S3 is equal to P3 XOR of C3. Okay. So likewise, we can determine sum and carry of each full adder, and moreover all carries of the all full adders are expressed in terms of the known quantities. What are the known quantities here? P3, G3, P2, G2, P1, G1, P naught, G naught, and C naught is also known. In general, C naught is grounded, that is equal to 0. Okay. So in that way, we can determine all carries well ahead of the addition operation. That is what is carry look ahead adder. Okay, now similarly for ith full adder. Okay, for ith full adder, carry Ci plus 1 is equal to AI Bi plus AI XR of Bi into Ci. What is AI Bi? That is equal to Gi plus what is AI XR of Bi is equal to Pi into Ci. This is for the ith full adder. Okay. Now, if we draw, circuit for the logic circuit for the 4-bit adder with carry look ahead adder, carry look ahead logic. Okay, that is, so this is the carry look ahead logic. So here the inputs are A3, B3, A2, B2, A1, B1, A0, B0. First we will find generate, then propagate G3, P3 from these two, G2, P2, G1, P1, G0, P0, and C0. C0 is the input here. Okay. So now carry look ahead logic. This is not the carry look ahead adder. Why? Because here we found out only carries by using this logic. Now we have to determine sums also. So after getting the, all carries here, now we can determine easily sum operation, that addition operation. That is what is sum output of the adder. So now what is S naught is equal to A naught B naught, A naught XR of B naught XR of C naught. That's why from here G naught we are getting A naught XR of B naught into XR of C naught. This S naught is equal to A naught XR of B naught XR of C naught. Similarly, what is S1 is equal to P1. What is P1 is nothing but this one. I'm sorry, I wrote it in reverse manner. These are not, this is P1, this is G1. Wrong actually. Propagate. So what is propagate here? Propagate means XR operation. Here, this figure is wrong. Try to correct this one. So here it is. P1, G1, reverse. I wrote it in reverse manner, reverse order. So this is P naught, G naught, P1, G1, P2, G2, P3, G3. Okay, this is P3, this is G3. So here, this one, P2, G2, P1, G1, P naught, G naught. Okay, here this is correct. In this, I followed the same order even after changing the XR and indicate here. Okay, this is P2, G2, P1, G1, P naught, G naught. Okay, for S naught, what we require, we require P naught. What is P naught is equal to A naught XR of B naught. Okay, A naught XR of B naught into B naught XR of C naught. So for S1, P1 XR of C1. What is P1 is equal to A1 XR of B1. So that is A1 XR of B1 XR of C1. What is S2 is equal to P2 XR of C2. What is P2 here? P2 is nothing but A2 XR of B2. So now S2 is equal to A2 XR of B2 XR of C2. Similarly, what is S3 is equal to P3 XR of C3. So what is P3 is equal to A3 XR of B3. Finally, S3 is equal to A3 XR of B3 XR of C3. Okay, this is how we can implement or we can perform the 4-bit addition by using carry look ahead logic. Okay, carry look ahead logic means we can determine all carries of the full adders well ahead of some operation, addition operation. Okay, so then in this way we can implement, we can perform n-bit n-bit addition using carry look ahead and logic. Okay. So now this is the for any simply for any I plus one full adder. Okay. So carry look ahead logic will determine the all carries. So here inputs are AI, BI, this is GI, this is PI. So then it will determine all carries. Now to determine the sum of the particular level, particular full adder, what is the problem here? Carry propagation delay. Okay. So, I mean, even though the input bits are ready, it cannot perform the addition operation. Why? Because it has to wait for the carry from the previous ladder. To get rid of that problem, we use carry look ahead logic. In carry look ahead logic, by this will determine all carries of the all ladders well before the addition operation. Okay. Any doubts? Please unmute and speak. So now you should know. I mean, you might have understood what is the difference between ripple carry adder and I mean, n-bit adder. That is n-bit ripple carry adder and n-bit adder with carry look ahead logic. Next one is binary multiplier. Already we know how to equal to 6 or 12 into 12, that is equal to 144, like that. In the similar manner, we can also multiply two binary numbers. That is what is binary multiplication. Okay. So if you see in mathematics, to multiply two numbers, when we are multiplying two numbers, one number is known as multiplicand, other one is known as multiplier. Similarly, for binary numbers also, when we consider two binary numbers, one binary number is known as multiplicand, other binary number is known as multiplier. Okay, in this binary multiplier, this is also a combinational logic circuit which performs the multiplication of two binary numbers. Now in this we will study 2-bit multiplier and 3-bit multiplier. Okay, 2-bit multiplier means we'll multiply two binary numbers. Each binary number consists of 2 bits. That is what is 2-bit multiplier. So what is the output of the multiplier? Multiplier output is product term. Okay, so here the inputs are A and B. A is consisting of 2 bits and B is also consisting of 2 bits. That's why this is known as 2-bit multiplier. Okay, so A is equal to A1 A0, B is equal to B1 B0. Now here, if we see, this is 2 power. This is in binary base 2. If it is in base 2, this is what is the position here? 2 power 0. This is 2 power 1. So when we multiply these two, what is the maximum binary position? That is 2 power 1. This is 2 power 1. When we multiply these two, that is 2 power 2. Okay, so 2 power 0, 2 power 1, 2 power 2, and at the end we may also get carry. That's why 2 power 3. So when we multiply two 2-bit binary numbers, at most we will have 4 bits at the output. That is what is the product. The product consists of at max 4 bits. Okay. Now we'll see how to. Now that's why a product P is equal to P0, P1, P2, and P3. Now we'll see how to multiply them. This is similar to the, decimal numbers multiplication. So here we are considering two binary numbers A and B, A1, A0, B1, B0. So first we have to multiply these two A0, A0 with B0 with A0 and B0 with A1. Next we have to multiply B1 with A0 and B1 with A1. So when we multiply B0 A0, that is the result is A0 B0. When we multiply these two, the result is A1 B0. And similarly, so when we multiply these two, this is 2 power 0 position, this is 2 power 1 position, we will get the result in 2 power 1 position. That's why we are using class mark here. Okay, so A0 into B1 here. And when we multiply A1 B1, this is 2 power 1 position, this is in 2 power 1 bit position. So 2 power 1, 2 power 1, that becomes 2 power 2. That's why A1 B1 is in 2 power 2. Okay, so A0 B0 direct, and we have to add these. We have to add these two. That is A1 B0 plus A0 B1, and we may also get some carry. That carry we are treating it as C1. That C1 goes to the next one. So here, what are the bits we have to add? We have to add C1 plus A1 B1. We may also get carry. That is C2. And C2 goes here. C2 directly comes here. Result. Okay. Now, if we see, if we write down in terms of P0 P1, this is P0. P1 is equal to A1 B0 plus A0 B1. Okay, what is P2 is equal to P2? P2 is equal to A1 B1 plus C1. Okay, so at this level, no carry. In this level, A1 B0 plus A0 B1. This is simply addition. Addition means we'll have sum and carry. Okay, so what is the result here? P1 is equal to A1 B0 XOR of A0 B1. comma carry C1. So next, what is P2? P2 is sum of these two, that is C1 plus A1 B1. What is P3 directly, that is equal to C2. So at this level carry is C1, at this level carry is C2. Finally, what is the P3 is equal to here? We don't have any other term, that's why the carry becomes the P3. Okay, now when we draw logic diagram for this one, okay, so first P naught is equal to A naught B naught, that is the end operation of A naught B naught gives you P naught. Next one, A1 B naught A naught B1. Okay, so when we are adding these two bits, means we need half adder. Half adder, what is the sum operation? Sum operation is nothing but A1 B naught is one bit, XOR of A naught B1 is the other bit. So that's why XOR of A1 B naught and A naught B1 gives you the sum P1. What is the carry here? Already we know for half adder, what is the carry when inputs are x and y? So sum is x XOR of y, carry is equal to x into y. Okay. So now what is this? C1 is equal to product of these two. That is A1 B naught into A naught B1. That gives you the carry. That is what is the product of these two, this one and this one. Product of these two bits gives you the carry expression. This is nothing but the half adder. Okay. For this operator, what are the input bits? One input bit is A1 B naught, other input bit is A naught B1. Okay. What are the outputs? P1 and C1. P1 is the sum output, C1 is the carry output. Now similarly, when it goes to next one, that is P2, A1 B1 plus C1. So A1 B1 means end operation. So what are the bits available here? A1 B1 is one bit and C1 is other bit. So we have to add these two. Means what is the result? Result is sum and carry. Sum is nothing but C1 XOR of A1 B1. What is the carry is nothing but A1 B1 into C1. So that's why product. This is C1. This is A1 B1. The output is C2 is equal to P2. Please unmute. P2 is equal to A1 B1 into C1. That is P2 is equal to C1 XOR of A1 B1. That is this is the sum expression. This is the carry expression of a half adder. Okay, why it is half adder? Why half adder is sufficient here? We are having only two input bits. For two input bits, for two bits, half adder is enough. Okay. So the, I mean, this is how we can draw the logic diagram or logic circuit of 2-bit multiplier. Once again, let me explain. So these are the two binary numbers, which each binary number consists of 2 bits. That's why this is 2-bit multiplier. A1 A naught, B1 B naught. So here A naught, B naught into A naught and B naught into A1, B1 into A naught and B1 into A1. That is what is written here. And at this level A naught B naught, at this level we have to add these two, A1 B naught plus A naught B1, and we may also get carry. This carry goes here. Again here we are adding two numbers. This is the sum and this is not the sum. This is simply we can say addition. We may also get carry. So now we can write down P0, P1, P2, P3. So here, strictly speaking, this is if this P1 is sum, here instead of writing R expression, we have to write down the XOR. A1 B0 XOR of A0 B1. So here also we have to write XOR operation. A1 B1 XOR of C1. Okay. So this is how we can draw the logic diagram. So here, I mean, so why this sum and carry? So these are the two input bits. We have to add these two. That is what is half adder operation. Two bits. So when we adding two bits means that is nothing but half adder operation. So one input bit is A1 B0, other input bit is A0 B1. So the sum expression P1 is equal to A1 B0 XOR of A0 B1. Carry is nothing but A1 B0 into A0 B1. End operation. Similarly at this level also. Okay. So this is the example 1110. When we multiply 1110, 0 into 10, 0 into 10, 1 into 1, 1, 1 into 1, 1. So this is 2, 3, this is 2. When we multiply 3 into 2, that is 6. That is nothing but 0, 1, 1, 0. So now we are checking with the circuit, whether the circuit is giving the same answer or not. So A naught B naught means A 1 into 0, that is 1. So P1 is equal to A naught B1 XOR of A1 B naught. So A naught B1 XOR of A1 B naught, that is nothing but 1 XOR of 0, that is equal to 1. What is carry? A naught B1 into A1 B naught, that is equal to 1 into 0, that is equal to 0. Next level P2 C1 XOR of A1 B naught, A1 B1. C1 is 0, A1 B1 is nothing but 1 into 1, 1, 0 XOR of 1 is 1. Okay, C2 is equal to C1 into A1 B1, that is equal to 0. That is P3 is equal to 0. Okay, so I mean, if you see this is not equal to 1, this is equal to 0. Try to correct this one. This is 0. So that is nothing but 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0, nothing but 6. This is 0, this is not 1. Mistake. Try to correct. So this is about the 2-bit multiplier. Now next we will see 3-bit multiplier. Similar to the 2-bit multiplier, we can also perform the 3-bit multiplication of two binary numbers. Okay, multiplication of two binary numbers. Each binary number consists of 3 bits. That's why this is nothing but 3-bit multiplier. Okay. So here A is consisting of 3 bits, A to A1, A0. B is consisting of 3 bits, B to B1, B0. So here this is 2 power 5. 2 power 0 belongs to P0 and 2 power 5 belongs to P2. Okay. So now when we are trying to multiply two 3-bit binary numbers. Okay, that is A to A1 A0 and B to B1 B0. So here B0 with A0, B0 with A1, B0 with A2, that is A0 B0, A1 B0, A2 B0. Similarly, B1 with A0, B1 with A1, B2 with A2, B1 with A2. So that's why A0 B1, A1 B1, A2 B1. Third level, B2 with A0, B2 with A1, B2 with A2. Already I explained why we have to start this from this position. When we multiply B2 with A0, A1, A2. Why? Because B2 means 2 power 2 bit position. This is 2 power 0. Finally, the result will be 2 power 2 bit position. This is 2 power 0 bit position, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. Okay, so that's why we have written like this. Then afterwards, this is A0 B0. This is A1 B0 plus A0 B1. Here is C1. This goes here. So here 4 bits. So C1 plus A0 B1 plus A1 B1, C0 plus C1 plus A1 B1 plus A0 B2 plus A2 B0, and the carry will be C2. Okay, again similarly here. Finally, the carry C4 comes to directly P4. Okay. Now we are not trying to implement this directly. Why? Because so here we have to add 4 bits. So at max we are available with 3-bit addition, that is full adder. To add 4 bits we can't use full adder. Full adder is for only adding the 3 bits. That's why we are not going to implement this 3-bit multiplier directly. So we'll break into two parts. Okay, so what are the two parts here? So instead of implementing whole thing at a time, first I will implement this portion. So this portion, so clearly observe my cursor is moving like this. So this portion only. So A2 B0, A1 B0, A0 B0, A2 B1, A1 B1, A0 B1. So first of all, I will try to implement this portion. Then after implementing that, I will add the result to the remaining portion. Okay, first we will try to implement this portion. Then after getting the result, that result will be added to remaining portion, and that will give you the final result. Okay, why? Because direct implementation of this is not possible. Why? Because we are having only full adder, which allows only 3-bit addition. So here we want 4-bit addition. That is not possible with the full adder. That's why we are breaking this into two parts. Then we'll proceed. Okay. So now this is how we can break A2 B naught, A1 B naught, A naught B naught, A2 B1, A2 B1, A1 B1, A naught B1. Okay, this is class. Okay, so here it is. I am treating this as S naught. So A1 B naught plus A naught B1. I am treating it as S1, and the carry is C naught, CA instead of nothing C naught, CA. The CA goes to next level. So here we are adding CA plus A2 B naught plus A1 B1. the carry will be CB. This goes to next position, next level. Here what we have to add? We have to add CB and A not B1. A to B1. So here B1 is not written. Try to write B1 here. So the carry is C3. This goes here directly. So S4 is equal to CC. Okay. So now S naught is equal to A naught B naught. S1 is here. S2 is here. S3 is here. S4 is here. Now we will see how to implement this. For this one, first draw line that is B naught. So this is what is the result here? A naught B naught. What is the result here? A naught B1, A1 B naught, A naught B naught. Here it is A1 B naught. Here it is A2 B naught. So first level. So this level A naught B naught, A1 B naught, A2 B naught. So this is A naught B naught. This is A1 B naught. This is A2 B naught. Second level A2 B1, A1 B1, A naught B1. So here write down one line like this. That is B1. So this is A naught B1, A1 B1. This is A2 B1. This goes here. I'm sorry. This goes here. Okay. I mean A2, I missed here. For this one, for last full adder, what are the inputs here? One input is this from here. I'm sorry. I mean forgot to draw. So draw line from here to here. One input. That is. So if you see here, what are the inputs here? CB and another input is A2 B1. So this is A2 B1 comes here and another input is CB. Okay. So now after drawing like this, now first full adder. For first full adder, I mean, even though it is 2 bits, let us consider full adder only. I mean, nothing to worry. Other input will be 0. Okay. So now for first one A1 B naught plus XOR of A naught B1. A1 B naught XOR of A naught B1. So that is S naught is A naught B naught. For first full adder, what are the inputs here? A1 B naught and another input is A naught B1. A1 B naught, A naught B1. Okay. So what are the outputs here? S1 and CA. We see S1 and CA. Sum is S1 and CA is the carry. Okay. Carry, this is the carry output, sum output. For second full adder, what are the inputs? So for the inputs are CA, A2 B naught, A1 B1. CA, A2 B naught, A1 B1. So this is A2 B naught, this is A1 B1, and the input is CA. CA, A2 B naught, and A1 B1. These are the three inputs. What are the outputs here? So the outputs are at this level are what are the outputs? S2 and CB. So some output is S2 and carry output is CB. For next one, what are the inputs? CB and A2 B1. This is A2 B1. So the inputs are from here, draw one line here, that is A2 B1. So another input is CB. What are the outputs? The outputs are S3 and CC. So here the sum output is S3, carry output is CC. We don't have any furthermore full adders. That's why this CC go to S4. So S0 is A naught B naught. S1 is I mean full adder operation. Okay, here S2, S3, and S4. So now we will use this result for next one. Okay, so write down S0, S1, S2, S3, and S4. Then what we have to do? We have to put class mark, 2 class marks here. So that's why we are not using S1, S0. For remaining 3, we will write down these three, A2, B2, A1, B2, A0, B2. Okay, so for S1, S0 class mark, for S2, below S2, A0, B2, below S3, A1, B2, below S4, A2, B2. Okay, now we will try to add this S1 direct, S0 direct, S0 directly goes to P0, S1 directly goes to P1. What about S2 plus A0, B2, and carry is CD and sum is P2. This CD goes here. At this level, what is the addition? We have to add CD plus S3 plus A1 B2. The result is sum is P3 and carry is CC. CE. CE goes here. What is the sum operation here? CE plus S4 plus A2 B2. The sum is P4, carry is CF. This CF goes here. We don't have any further bits here. That's why this CF directly goes to P5. This is how we can get P0, P1, P2, P3, P4, and P5. This is the product term. Okay, final expression. That is the output of the 3-bit multiplier. Okay. So now we'll see how to extend this diagram. So here from this now will the next part of the diagram. So for next part of the diagram, S1 is not directly available. Remaining part means here. So here we draw one line, that is B2. So A not B2. Here also I forgot this one. Sorry, I'm sorry. Please draw a line here. This is A not B2. This is A1 B2. This is A2 B2. For S1 is not direct. For this one, next one, what are the inputs? S2, A not B2. S2, one input is S2, other input is A not B2. This is A not B2. What are the outputs here? P2 and CD. Some output is P2, carry output is CD. Okay. For next level, what are the inputs? CD, S3 and A1 B2. CD, S3 and A1 B2. And what are the outputs? P3 and CE. Okay, that is some expression is P3, carry is CE. For next full adder, what are the inputs? CE, S4 and A2 B2. So here S4, write down the S4 here. I forgot to write inputs for this one. One input is S4, other input is A2 B2. So from here, write down the line like this, A2 B2. And what is the other input? That is S4. What are the outputs? The outputs are P4 and CF. Okay, P4 and CF. We don't have any further colliders. That's why the CF goes to P5. Okay, so this is how we can perform the 3-bit multiplication. Two 3-bit binary numbers multiplication. That is what is 3-bit multiplier. Okay, let us see one more time. Just write a brief. So first of all, we have to write like this. Then don't try to draw logic for this expression directly. Why? Because here we are having 4 bits. So at max we can add 3 bits by using full adder. That's why we are not trying to implement this whole at a time. Instead, what we can do, we can divide into 2 parts. So first we consider this part. Okay, above part. Then this is the above part. Okay, here we are having this some expression, some outputs and carry outputs. Carry outputs are CA, CB, CC, CA, CB, and CC. The some outputs are S0, S1, S2, S3, and S4. Okay. Now, after getting these expressions, we will again add these two remaining part. That is, this is the part remaining here. Okay, and by putting class marks, why? Because S1 is not directly we can use. So this S0 goes to P0, S1 goes to P1. Remaining again addition. Okay, so this is how we can implement 2-bit multiplier and 3-bit multiplier. So with this, we are done with the module 2. Next class, we will start module 3, that is sequential circuits. Okay, there first of all we will see what is the difference between sequential and combinational circuits, and also we will see the difference between synchronous sequential circuits and asynchronous sequential circuits. Then we will move on to next topics. Okay, so this is about the carry, look ahead adder, and binary multiplier. So if you are having any doubts, you can ask. Students, please. I don't know, out of 64 students, at max 30 to 35 students are attending the class. I don't know. So these are important topics. If you miss, that is your problem.
Excuse me, sir.
Okay, tell me.
Sir, can you share the recording of this session?
Sure, definitely. I'll put it in YouTube. You just search in YouTube.
Okay, sir. Thank you.
Okay, thank you. Any other doubts, please? Please